Hi, my name is Asim,
My name is Ashwin.
and this is our course project for this class. So we will be focusing on a card game called Bridge. Bridge, unlike other card games, is more complex, as it's a partially observable Markov decision process, and it's also an imperfect information game.
One of the main motivations for us choosing this project was that we've seen more and more of the feature extraction delegated to neural networks as opposed to human experts. Earlier this year, Facebook AI came out with a paper in which they trained bidding agents on raw card data to perform very well in the bidding phase of the game Bridge. So we decided to apply a similar feature extraction technique with a DQN on the trick-taking portion of the game Bridge.
So like Ashwin said, there's two sides to the game, bidding and trick taking. We just focus on the trick taking portion of the game. So what is trick taking, you might ask? Trick taking is when four players going counterclockwise and play a card out of their hand. So the player that plays the highest valued card out of their hand gets the point. But since Bridge is a team game, the team that plays the highest valued card in the pile wins that trick, so they get a point for that. So the ideal way to play Bridge is to try to win as many tricks as possible, and that's how we dumb down this version of the game. So some of the information we keep out of these rounds include our card information, so the cards we have at our hand, the pile information, so what cards people have played in that pile, and then a history of tricks, so cards that have gone into the pile from the players in terms of history. And we put all this information into a feature representation that we will talk about. And this feature representation goes into our DQN. So before we go into our DQN, we're going to talk about the environment we created and give you a walkthrough.
So we created an OpenAI gym environment and modified it a bit to handle a multi-agent sitting, since that's not handled natively by gym. So the modification we made is that within each trick, each player has to call the play method first, and once all players have called the play method and played a card, then we call the step function, which is when they get the reward. And the reason for this is that rewards can't be assigned until all four players have played in a trick.
This was also the main problem of our project as well. We weren't able to find a Bridge environment, so we had to create our own. So since we weren't able to find one, we're also going to contribute this project and release it open source. So now to go into our model a bit, we trained a DQN with a neural network that had a one hidden layer. And some of the parameters of the DQN we had were a 0.0001 learning rate, and then we had a replay memory of size 130. So this means that after every 10 rounds, the replay memory gets updated. So now, when training the DQN against a random agent, this is how it performed. So it performed very similarly to the random agent, and if this was trained for more episodes, they would both play this at the same rate.
So when we trained the DQN against a smart agent, we saw that it consistently performed worse than the smart rule-based agent that we created, even after 70,000 episodes of training. And we predict that even if we trained it longer, it would never converge to a value approximation competitive with the smart agent.
So after training the DQN against a random agent, we tested it against different agents as well. So we tested against a random agent, smart agent, a DQN trained with the smart agent, and then we also trained DQNs among with other DQNs. This was a rudimentary implementation of self-play.
So we saw both in the DQN trained against random agent setting and the DQN trained against a rule-based agent setting that they performed only about as well as random even after thousands of episodes of training, about as well as the other DQNs, and far worse than the rule-based agent that we created.
So we saw similar results when the DQN against other DQN agents were trained in our method of self-play, and this is how it tested against other agents. So in conclusion, what we found was that our training methods had suboptimal results. So in the future, some things we would like to test are more things that go into self-play, specifically neural fictitious self-play.